want to cover a chapter, as usual in the book. I just wanted to cover some machine learning extra credit projects tonight. Some of you may have already seen them. And the other thing I want to tell you about is a lot of special events coming up. There is a Securing the Internet of Things talk coming up in 2 days. This is worth extra credit. It's on a Thursday night when I no longer have a class, so maybe not very many people will come, but it is worth extra credit. And they say it's going to include like a hands-on exercise or something, so it should be pretty fun. We'll see what happens. And there are some guest lectures coming up. Caitlin is going to talk about radio frequency attacks. I know this will be great. Her stuff is amazing. She's a professional pen tester for Amazon. She's basically part of an APT. And she had an internal conference, and she developed like 4 new radio frequency attacks just for this conference. So she's going to deliver it. So this, I highly recommend. This will be on November 28th.
How advanced do you have to be to attend these kind of...
How what?
How advanced do you need to be in hacking?
Not very. She's very good at making it understandable. Her stuff is always very good. And Kaz, by the way, they were both my students, and they both got jobs in Amazon. Kaz is going to talk about Kubernetes, which I'm very interested in because I'm going to be a Kubernetes admin, and by then I'll be actually administering a Kubernetes instance, and I'd like to hear what he has to say about it and learn more about it because Kubernetes is very complicated and it has a lot of security problems. So anyway, I highly recommend tuning into those things towards the end of November. And CPTC is coming, so I'll be out of town that Saturday down in Stanford with the team. It's not anything you can tune in remotely, unfortunately. There's no way to watch or anything, but the students on the team will be there competing, and so we'll see how they do. Anyway, those are special things coming up. And so for this tonight, I just wanted to show you a couple of machine learning projects because I think it's very important enough that I've thrown it in all my courses. And I added a couple extra credit projects here. So if you haven't already done these, if you've taken my machine learning course or you might have seen these before, if you've already seen them before, then you feel free to just ignore what I'm saying tonight. But if you haven't, everybody should start learning machine learning. It is super important. It's going in every tool. It's in every online service. It's just everywhere. We should all be getting on board with it. And I just proposed this for a conference. And they said, oh, are you teaching the Intel machine learning course? And I said, there's an Intel machine learning course. So I looked at it, and I am, in fact, teaching the Intel machine learning course. There's just standard stuff. I looked at what they're teaching, and it's the same thing I'm teaching. I just found the best textbook. It's pretty much the same lessons. Anyway, so here's the first couple things to do, and this is using Google tools. So I'm just going to demonstrate these 2 projects to get you started. There we are. So first, you use Google Colab, which is great. Google Colab gives you a free Python environment with GPUs and TPUs if you want them, although we're not going to use them. So you can't beat the price, and you don't have to have anything installed locally. You just make a new notebook. Now you can execute Python commands right here. It will hang up on you after about an hour, and you can only have a certain number of them saved before they throw them away unless you pay them money. But you can do a lot for free, which is the right thing for me. So here, you import TensorFlow. TensorFlow is the library. There are a couple of popular machine learning libraries, and this is one of them, TensorFlow. You import it and then just see which version you have, and the textbook I got this from said it had to be a certain version, not too old, and of course everything in Google Colab is right up to date. So, all right, so it imported it and it gave me a version number. I don't really care which version number it is. Okay, so now this is the essence of machine learning. This is what got me very excited. Like I said, I did this 50 years ago. I'm not kidding. First thing I did was curve fitting. But back then, I did it using analytical techniques that were developed before computers. But the task of putting a curve through some data was very interesting, and I learned a lot of techniques, and that's what we're doing here. So suppose you have some numbers like this. You do some kind of measurement of something, like temperature or pressure or something, and you have X going through there, and here's your Y, the thing you measure, -3, -1, 1, 3, 5, and 7. So there's some kind of relationship. The first thing you notice is when X gets bigger, Y gets bigger. And then if you look at it more carefully, you say, well, every time X goes up by 1, Y goes up by 2. So after a while, you can figure out Y is 2X minus 1 is the way you put a line through those data. Now, this is something that it used to take humans to do, human intelligence to spot a trend and deduce what is the equation to go through that trend. But this is what the essence of machine learning is. The machine will figure this out. So you do not put this code anywhere in the code, no Python or anything. It figures it out from the data. That's the essence. This is the thing that is intelligence. That's machine intelligence. So here's how you do it. This code will do that job because there are, just this is why everybody uses Python. There are libraries that do all the work for you. All you have to do is learn how to use the library. So I put another block of code here. So this is going to import TensorFlow, which is already there, and NumPy, just a number library, and then sequential and dense. And what it's going to do is make a neural net, including sequential operations, with only one operation, which is a neural net containing one neuron. This is the simplest possible neural net, one neuron. Now, a neuron, here's a neuron. And this is modeled after the real neurons in our brains, but you have data come in, and then it does some kind of calculation on all the inputs and creates an output. But in this case, there's only one input and one output, and all it's going to do is a linear calculation. So it's going to take mx plus c, a slope plus an intercept, times this to produce that. And it's going to adjust these to minimize the error. That's what's going to happen here. So this creates a neural net with one neuron, and now I'm going to optimize it with standard stochastic gradient descent. Stochastic gradient descent, first you have to have a measure of error. The loss is the mean squared error, just what I used before I wrote computers. This is the classic one. If you take the square of the error and add it up, that has some wonderful statistical properties. It creates a convex curve, so there is a curve leading down to the minimum, and you don't have any local minimum or anything. So all you have to do is, this is the loss. It will now calculate which direction in parameter space would make it get smaller, and it will take a step in that direction. And it will take 500 steps. So it will take little steps hunting for the minimum. And then, all right, so then at the end, I'm going to predict the value of 10. Now, the right answer is 2x plus minus 1, so the correct y for 10 is 19, 2 times 10 minus 1. And just to see how good it is, that's how I'm going to measure it. So here we go. It now does 500 steps, trying to lower the loss with that one neuron. And so if you look back here at the start, it starts with a loss of 37 because it's terrible. It starts with just random guesses for the numbers, so it's not even close, but as you can see, it goes down, down, down. It adjusts the parameters and its loss is going down, 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 and after a while the loss gets very small, 0.4, 0.05, and if I do 500 epochs, 500 steps, it gets down to 10 to the minus 4, a very small loss because this data has no noise. It's possible to go perfectly through the data, so it can get very close. So after my 500 epochs, it gets down to 5 times 10 to the minus 5, and here's my prediction. It was supposed to be 19. It's 18.97, so it's very close, which is all very logical. I gave it a very simple problem. Yeah?
Can you visualize this stuff you said, like steps and what slope we're talking about?
Can you what?
Like what steps we're talking about?
It automatically chooses a value of the steps. It chooses some amount to vary the parameters by. And so it's going to vary M and C. So it starts with M and C random, and then it uses a technique which is pretty awesome called reverse propagation to find the slope, which has actually an analytical technique which works for multi-layer neural nets. I just learned about it. It's in my class. It figures out the slope in parameter space and figures out which direction in parameter space is going down, and then it takes a step in that direction. And it starts with a default small step.
What if we have 2 layers?
If you can have as many layers as you want. This is a discovery that was made. Yes, there is a formula for the derivative. In all the dimensions, you can have a multi-layer neural net like the ones used for large language models, and you can back propagate through it and determine analytically the slope. That is why this works. Otherwise, it would be impossible. So you can have 500 million parameters, and you can analytically find which direction will lower the error. And then you take a small step, and off you go. Until this was discovered around 2005, and until then, people gave up on neural nets. Like I said, I did it years ago, and we gave up because it was useless. Until we had this back propagation technique, there was essentially no way to make it work. because you couldn't find what direction would make it go down. You'd have to try them all, and it would just take forever.
So we might get stuck in local minimum and
Well, you might hit a local minimum, but the immediate problem is just to find the slope in parameter space, so you know which direction is good to move in. Now, it may be a complicated shape, so you don't just take big steps. You don't try to calculate where the end is. You just calculate what direction will make it go down, and you take a little step. And that's why you do 500 little steps. And you can hit a local minimum. That is a risk. If the steps are too small, you might get stuck in a local minimum. If the steps are too big, you might jump over the minimum back and forth. So those are both flaws that can happen. However, in the simplest case of a mean squared error, it's a nice bowl that just goes down to the bottom. There's no other local minimum. This particular problem is so simple that you will find the minimum. You're right on track. Anyway, so that worked pretty well. And so now we can see what it learned. Here, I'm going to show the weights it got. It determined two parameters. So here, I think I actually do the work again, which is not necessary, but it doesn't matter. All right. And at the end, I'm going to print the weights. You can print them. And so this is the first project I wrote, so here's what it got. Remember that it was 2x minus 1. And here's the parameters it found, 1.997, that's the 2, and this is minus 0.9929. So both of them are within 1% of the right value. So with 500 little steps, it found the best minimum. And all right, so, and it used default values for the step size and default, and we just chose 500 epochs kind of at random. So that's the simplest demonstration of learning. Now, if there's no noise, it's kind of ridiculous. Then you could just draw a line to any 2 points. So we add some randomness to it. I've just randomly changed some of these numbers. So let's try this. If I add some noise, then we'll see what happens. Let's go back to this code. This is why it's great to have this Python sandbox, because you can just change things. And run it again. All right. So there's the code I want. And I'm just going to comment out this one. All right, so there's the perfect code, but this stuff has got little errors in it. So now it's not going to be able to hit 0 error anymore. But there it goes. So the loss started at like 0.05, 0.04, 0.03. It's still getting pretty small, but it's not going to get down to 10 to the minus 5 anymore. The loss is the mean squared error, the vertical error. So the difference between the y predicted and the actual y. That's the standard one, too. And so now the loss doesn't get quite as small, but it does find 1.995 and minus 0.999. So it finds 2 and minus 1 pretty well, and the point at 10 predicts to be 18.9 when it should be 19. So again, it does a pretty good job finding the trend in the presence of errors. So now let's try fitting a non-straight line. Now we only have one neuron, and the neuron is only doing a straight calculation with 2 parameters, slope and intercept, so it cannot fit a curve. So this is not going to fit very well, but let's see what it does. So if I try to fit data that's not even following a line, it'll still try to find the best line to go through there, but it's not going to do a very good job. Let's see, I've got to get rid of that. Down here, comment out that one. There. So these are now, without noise, these are values on a curve. So now the loss is 10, 6, 5.
I mean, those for these points might be lower, but for the other, parabola, we are making a parabola this time, right?
Yep, it's a parabola, so it puts a line through it, and there's going to be a lot of error. You're never going to get the error very small. Like the smallest error you can get is about 4. And the first time, with the perfect data, it got it down to 10 to the minus 5. With the noisy data, it got it down to 10 to the minus 2. But with the curve, it can't get any better than like 4. And you can see the parameter is supposed to be 2x plus 1 is what I expect. You see, it's going to give crazy numbers. So it can't do a very good job fitting it. Now, I think I figured out how to draw pictures. Yeah, so here let's try a complex curve. And we can do a more complicated model. This is going to be a multi-layer neural net to fit a real curve. So this is more like it. So I'm going to clear out this old stuff. I'm going to move to trash, return, make a clean new notebook. I could just keep using the same old one, but since I'm doing a whole different problem, I'm going to make a different notebook. And here it is importing everything. That's what I wanted to see. So now it imports this library called Keras, which is really powerful. This is what you use to build your neural nets. And now it's not going to use just one neuron. It's going to have one neuron taking the input. Then it's going to have a hidden layer with 64 neurons and another hidden layer with 64 neurons, and then one output layer. This is how you do it. So it's going to take the input from here, and then it's going to have a layer of 64 neurons and then another layer of 64 neurons densely packed. So there's going to be hundreds of parameters. And it's still a linear calculation of all the inputs, but all the 64 in the first layer go to every one of the next 64. So the total number of parameters is very large. And then it's going to optimize all this with 100 epochs. And then we're going to see what it creates. It's going to plot the graph. So it's getting ready. And you can see what step it's on here. It's just still importing the libraries. Now it's down, it puts a green arrow by the command there. Now it's down to fitting the model. There we are. So here's the summary of the model. You can see the shape. The first layer has one neuron. The next two have 64 neurons. Those are the hidden layers because they're not connected to the input or the output. Here's the output. So the total number of parameters is 2 here for slope and intercept. And let me go back up, and 128 here because the 64 neurons each have slope and intercept. And here it's 64 times 64 times 2 because each one of these 64 feeds into each one of the next 64, and each one of those has a slope and intercept. So it's 4,160 parameters in this layer, and here 65 in this layer because it gets inputs from all 64 neurons, and then it can have an offset. So this is the total number of parameters is now 4,355. And so in that 4,355 dimensional space, it's able to use this fantastic technique of reverse propagation to determine which direction will lower the error and take a little step. And so now it all starts at 0.1 and it gets down to 0.02 and 0.01. And there it does a good job putting a curve through all that data. And so this is not an analytical curve that a human wrote. It learned this by putting weights in all those neurons. And that's why it's extremely powerful. Yeah?
How do you use this curve?
This curve is in fact like x times cosine x.
You predict some values?
Yeah, you'll see it here. I made that curve is in fact 0.1 times cosine plus 0.1 times random noise. So it's 0.1 x cosine x. That's why it's a cosine that gets bigger. And then I added some random noise.
But if we introduce like some really big values for x, the curve will fail, right? I mean, it won't give us.
You introduce what kind of values?
Like if we test for like bigger values of x, the curve will fail, right?
No, it'll follow it anywhere you send it.
I mean, because this way curve goes down, right? Can it go down?
Yeah.
The graph. Can you see the graph?
The graph, okay?
So yeah. So
Oh, I know what you're saying.
Yeah.
Oh, yes, we only have data to here. So if you want to predict what it's going to be over here, that's really not determined. There's not much of a trend here. If it was a straight line, you might believe you could extrapolate it here. I don't think I believe you could extrapolate over to here. You don't know. You'd need some data. I mean, what's it going to do? It could continue this line. It could bend back up. I mean, you don't have any evidence. That's a fundamental property. That's true of science too, by the way. But although the famous example is Newton. I mean, Newton watched how things fell on Earth, and then he extrapolated that to the moon and the stars. And people said, "You're out of your mind. How do you think your law, based on watching like rocks fall on Earth, applies to the stars?" But it did. So that is a huge leap of faith. He extrapolated from this much evidence way out there. But machine learning models don't have that
I'm
ability.
saying that because like if it was like if this was like stocks or something, we could have predicted the future values.
You could try. This is what people do, right? In the stock market, when the internet came out, internet stocks went up by like a factor of 10, and so did Bitcoin for a while, so everybody jumped in. For a while, it just kept going up and up. Then at some point, it crashes, and there was no clue, right? So that's the problem. You have a trend, and then you try to extrapolate the trend, but you really don't know. You don't know how long it'll go before it hits some limit. Anyway, so this is, you can see it did a pretty good job, and there are some flags to find here where you can try changing the parameters. Like now you can change the number of layers. You can get rid of one of the layers, and if you do, the curve will get less. Because of less parameters, it'll be less accurate. You can, and then you can vary, so here you can try various units. Like here, 32 units per layer and one hidden layer. Let's run that one. So if I try a simpler model, I only want one hidden layer, so I'll comment out one of these. And then I only want 32 units here, so it's a much simpler model. One hidden layer with only 32 units. And so now it's only got like 99 parameters instead of 4,000. So it's a much simpler model. It'll calculate much faster, but it's pretty crappy, as you can see. It doesn't really follow the data as well because I've simplified it too much. And anyway, you can play with this and get an idea how these neural nets work. It's good, clean fun. And
in the machine learning class, do we go over like how hidden layers and stuff like that work?
oh yeah, yeah. Let me. I'm going through this book here, and the best book is this one. I think that's the one I'm going through. So I think this is the one I'm going to check. I have to tell them that anyway. And I've been going through. Yeah, I'm going through this. The chapters are really very interesting. Let me get down to the. Yeah. Here we are. You learn the models, you learn support vector machines, decision trees. These are the simple types of models. Ensemble learning, dimensionality reduction is amazing. And then artificial neural networks, and then train deep neural networks. And we're not going to get all the way through, but at the end you actually make your own large language model, which you can do. You can do it in free Google Colab. You can make your own LLM, and you can train it on the entire works of William Shakespeare. And it learns to write Shakespeare. It's bloody awesome. So it is amazing. Now what I did, my focus was on security. So I didn't do just these projects. I made some hacking projects where you hack into the neural networks because there are various ways to trick them and poison them. And so I made some projects where you do attack them and then try to defend them. But mostly we're just making them work. But anyway, so that's the first thing I wanted to show you. And oh, I see some comments there. Let me go here and see what comments have been coming in the Twitch. If I can find the Twitch. Here's the Twitch. All right. Okay, Obama, switchblades, Y knives. Okay, good. People found the price of the knife. Okay. And the rest of this is someone wants to promote me. Okay, good. Just spam. Okay, good. So we're not important comments I was missing there. All right, so let me stop this recording, and I'll make a separate one.